if I want to measure the charge in a region, one way that I can do it is I can integrate the charge density over that region. If I take the charge density, rho of r, that's the charge density. If I multiply by d3r, that will be the amount of charge in this little box at position r of volume d3r. So that's a dx, a dy times a dz. And if I integrate this over d, this tells me the charge enclosed. So if I divide by epsilon naught, that is equal to this. I've just rewritten the charge enclosed in terms of the charge density. And now I want to make a new equation by saying that the integrand here must equal to the integrand there. But now let's be careful about something. If two integrals give me the same value, does that mean that the integrands are equal? No. Can you give me an example?
Depends on the domain.
It depends on the domain, absolutely. Fantastic. Is everybody happy with that idea? If you have two integrals that give you the same value, it does not mean the integrands are equal unless you know the integrals give you the same value integrated over any domain. Okay? And this equation here is true for any d. And because it's true for any d, we know the integrand here is equal to the integrand there. Is everybody happy with that idea, or is there anyone who would like me to say a few words? Happy? Good. So let's now equate this integrand to that integrand, and we learn that the divergence of E is equal to rho over epsilon naught, the charge density. And there we see it. The source of the electric field is charge. That makes perfect sense. Okay? This equation here is again true in electrodynamics. This is the differential form of that equation. This equation is called the integral form of the Gauss law. This is called the differential form of the Gauss law. These are one of Maxwell's equations. So if you want to write down the equations that govern all of electrodynamics, there are 4 equations. This is one of them. So this is the differential form of the Gauss law. And that again is an equation that's true in full electrodynamics. Now, at this point, we have a very good excuse to introduce what's called the Dirac delta function. Can I just see a show of hands? Who's worked with the Dirac delta function? You may call it the Dirac delta distribution. Have you guys seen the Dirac delta? You've seen it, Saga? Good? Okay, so let's discuss that now. I think this is a very good point to describe it. If we think about the divergence of E, for our point charge, so our point charge had E equal to 1 over 4 pi epsilon naught r squared times by q r hat. So this is the electric field for a particle of charge q at the origin. So we said when we calculated this divergence, the divergence is 0 everywhere except at r is equal to 0. When we want to write an equation for this, what we say this is equal to it's q over epsilon naught. That's the q over epsilon naught that appears. And now we multiply by delta of x, delta of y, delta of z. Okay? So who's seen this? Okay, good. So let me tell you what these functions are. Delta of x is equal to naught if x is not equal to 0. So delta of x is non-zero at one point. X equals 0, absolutely. If I integrate delta of x dx, let's say from -1 to 1, I will get 1. So it's non-zero at one point, and the area underneath it is 1. Are there some mathematicians here? How does that sound to you? So you've got a function, it's 0 everywhere except for one point. And the area underneath it is 1. How tall do you think that function has to be? Has to be infinitely high. You see? So let's think about it. So you can think about it as a limit as follows. So imagine you take a function that behaves like this. The height of this function is 1 over delta. That's the height. The width of this function is delta. What's the area under here? 1, because it's delta times 1 over delta. If we take the limit that delta goes to 0, how thin does it become? 0. So it's becoming very thin. How tall is it? Infinitely tall. Okay? So let me ask the mathematicians again. How do you feel? Not good? I can see you look like you're having a bad time. Not good? Okay. These things are not actually functions. They're called distributions. You can't do things with them that you can do with normal functions. You can't square them. Okay? So they're not nice things to work with. I mean, physicists love them. We use them all the time. But you have to be a little bit careful working with them if you don't want to get wrong results. And you have to be careful if you're a physicist or a mathematician. And you can often get the wrong answer just because you do something sloppy with the Dirac delta function. So I want to show you guys how do we define them as physicists, and I want to show you why we define them like that. So we use this, we say delta of x is equal to naught if x is equal to naught, and then we say if you integrate from a to b, you will get 1 if a is less than naught and b is greater than 0, and you will get 0 otherwise. Now, so I'm certainly not a mathematician, and one of the things that I guess maybe as a mathematician you wouldn't like is I haven't actually defined delta of x, right? I've just told you what you get when you integrate over it. I haven't told you what delta of x itself is. So when I've looked at mathematical books that have dealt with deltas, they always deal with it as a limit. So they talk about some sequence of functions, and the delta function is the limit of the sequence. And if you want to prove some results, you work with a sequence of functions, and you take some sort of a limit. As physicists, this is all we use. And let me show you the kinds of things that you can do. So let's say that you want to calculate the integral of delta of x, let's say x minus a is just some number, times by f of x dx. And let's say we're integrating, I don't know, from minus 10 to 10. Here's a number line, there's minus 10, there's 10, and let's imagine that a is some point inside the number line. So when I want to do this integral, the way that I do it is as follows. The first step, I write this. And what I'm using here, I claim that this is true. Why is that true? Good. When x is not a, this side is 0, that side is 0. When x is equal to a, the two are equal. Everyone happy? Does f of a depend on x? No. So, I can take it out of the integral. What is the integral over the delta function? 1, because a lies inside the region that I'm integrating over. So I'll just get f of a. Everyone happy with that? So actually, all that I needed to use was that property and this property. And that's all I ever use. I want to give you guys an example with the delta function, and I want you to tell me what the answer is. Okay, so I've heard 1, I've heard 0. What is this equal to? Cos of pi. What is the cos of pi? Minus 1. Okay. So this would give minus 1. Absolutely. How did you get that? Well, the only place where delta of x minus pi is non-zero is when x is equal to pi. So this is the cos of pi. You can take it out of the integral, and then the integral gives you 1. Next one.
But in the condition where that a will be less than 0 and less than b, here our a is not less than 0.
Okay. So that 0 there here, this 0, that's where the delta function's argument is 0. Do you agree? So I want the argument of the delta function to be 0 inside the integration region. Where is the argument of this delta function equal to 0? When x is equal to? Does pi lie between 2 and 4? Okay, so we are integrating over the point where the argument of the delta function is 0. Happy with that? Good. Okay. Now I want you guys to calculate this one. Minus? Minus 1. Is that what you say, minus 1? Minus 1, 0. It's minus 1. Cosine pi squared. Okay. Are we doing careful mathematical calculations or are we guessing wildly? Okay, now, in actual fact, what's going on here? Here is an integral. Inside there's a delta of x squared, and I'm integrating dx. No one told me what that is. Look, this is delta of x dx. So my integration variable here is the same as the thing that sits inside the delta function. Integration variable is not the same as the thing that sits inside the delta. So let me fix that first. Let me say u is equal to x squared. If I do that, then I get a delta of u minus pi squared. I will have a cosine of the square root of u, right? But now I need to worry about dx. If I look at this here, du is equal to 2x dx. So that tells me dx is equal to du over 2 square root u. So I can put there 2 square root u du. And where do I integrate from? 4 to 16. Where does the delta function give me something that's non-zero when u is equal to pi squared? So I'll get the cos of pi over 2 pi, because the square root of pi squared is just pi. And then I've got the integral from 4 to 16 delta of u minus pi squared du. And what's that integral equal to? This integral is 1. The cos of pi minus 1 minus 1 over 2 pi. Okay? The trick with working with the delta is nicely illustrated in this example. When you use the definition, what you're integrating over has to be the same as the variable that's inside the argument of the delta function. And once you've arranged that, then just use the definition of the delta on the top board. Okay? So that's the crucial point. We need to make the measure, the variable appearing in the measure, the same as what appears inside the argument of the delta. And as long as you've done that, you're in business. And those are the rules for working with the delta function. And then you can see we can write a formula for our divergence in terms of delta functions and the charge of our particle. So that's why it's useful. This is why we sometimes use delta functions. To write down something that's non-zero at one point, but still has a finite area underneath it. Yes?
I was seeing the variables would be the same, but it's just that the degrees were different. Let's say the variable in there should be power.
So, can you see dx matches the variable inside the delta function?
Yeah.
Here, the variable inside the delta function is x squared. The integration variable is x. That's the mismatch. So I want to make my integration variable the same as the variable inside the delta. Here, the variable inside the delta is u, and I'm integrating du. So that's what I did in that step. Did I answer your question? Good. Yep.
From that definition, you have been integrating from A to B.
Yes.
And they will show that the integral will give 1 only if we have 0 between A and B.
That's correct.
Right? Between 1 and 16, there is no 0, still we are getting 1, right?
Okay. Do you want to answer this question? No? You don't want to? Will you answer it? Okay, I'll answer it. Here's the point. This 0, okay? The reason why we wanted 0 to be there is because that's where the delta function hits 0. Okay? So what's important is not the 0, it's where the delta function hits 0. Now look at this delta function over here. Where does this delta function hit 0? When u is equal to? Pi squared. How big is pi squared? 3 point something something times 3 point something something, about 9. Does 9 lie between 4 and 16? Yes. That's why we get something non-zero. Okay? Happy? Good. Okay. Good. Okay, guys, so that's the delta function. I will put up some problems on the web page involving the delta so that you can get some practice in integrating with it. This delta function appears all over the place. Get used to working with it because you're going to see it a lot. Okay? We're nearly finished today. Just one thing left, which is? The joke. Okay, now, today's joke is not about a mathematician or a physicist. It's about a zoologist. Now, this is about an Irish zoologist, and I don't mind telling an Irish joke because I'm part Irish. So if you're part Irish, you can tell an Irish joke. So this is about an Irish zoologist, and he's studying a frog. So he takes the frog and he puts it on the table, and he bends down and he shouts at the frog, "Jump!" And the frog jumps. Then he writes in his book, the frog was told to jump, and it jumped. Then he takes some scalpel, and he takes the frog, he gives it some anesthetic so the frog won't be hurt, and he cuts one leg of the frog off. So now the frog only has 3 legs. He puts the frog on the table, he bends down, and he shouts, "Jump!" And the frog jumps with his 3 legs. He writes down in his notebook, 1 leg was removed, the frog was told to jump, the frog jumped. Then he puts anesthetic on the next leg, he removes the next leg. So the frog now only has back legs. Then he bends down and he shouts at the frog, "Jump!" And the frog jumps with his 2 back legs, but he still goes. He writes down, the frog was told to jump, the frog jumped. Then he puts some anesthetic, he removes another back leg. Now the frog only has 1 leg. So he bends down and he says to the frog, "Jump!" And the frog kicks with 1 leg and he jumps. He says, another leg was removed, the frog was told to jump, the frog jumped. Then he puts some anesthetic, he removes the last leg, he puts the frog down. Now the frog is sitting there, he doesn't have any legs. The zoologist bends down, he says, "Jump!" And the frog just looks at the zoologist. Then he bends down again, he says, "Jump!" And the frog just looks back at the zoologist again. So the zoologist writes down, the 4th leg was removed, the frog was told to jump, and the frog just sat there. And then he says, conclusion. After the 4th leg was removed, the frog went deaf. Okay guys, that's it for today.